Hi dear students, welcome to the next session of magnetic effect of current. Okay, so last class we have studied about Lorentz force. Lorentz force is a combination of electrical force and magnetic force. F L equal to QE plus QEB. So now today's sessions we are going to see what happened to a charged particle if it is moving in a combined electric and magnetic field. Okay, so let's go and see the heading. First one, motion of a charged particles in a combined electric and magnetic field. So motion of a charged particle in a combined E and B electric and magnetic field. In short, I am writing in a combined electric and magnetic field. So motion of a charged particle in a combined electric and magnetic field. So there are different cases we are going to see will be here, and this is very important in point of view of entrance examination. So different cases. Okay, so let's start with the case number 1. First case. So case number 1. Charge Q we are taking as a positive Q. So plus Q, which means Q is at rest in a parallel E and B. So what does this means? Electric fields and magnetic fields are acting in parallel direction, and we are placing a charge over here. So let's consider we have an electric and magnetic fields, both are parallel. Okay, we will take it as 2 lines, that is enough. So electric field vector, magnetic field vector, 2 lines, we keep a charge. So initially the charge is at rest. Okay, so this is a charge, Q is at rest. Okay, so Q is at rest initially. We can say Q is rest initially in a parallel electric and magnetic field. So according to Lorentz force, FL equal to QE plus Q into V cross B. Magnetic force plus electrical force equal to total force. So what will happen? When a charge is placed in this direction, electric field will start to pull the charges in the direction of electric field intensity. So electrical force will be there. Because of the electrical force, the charge is moving with a certain velocity called V. Okay, now we know V and B are parallel to each other. So I can say V is parallel to what all the things? Parallel to E and B. V is parallel to E and B. So now the Lorentz force FL will be equal to QE plus Q into V into B, angle between velocity and magnetic field. Velocity is parallel to magnetic field, same line. So what is the angle? Become sine of 0. So there is no magnetic force, only electrical force. Total force equal to electrical force. Magnetic force vanishes because velocity is parallel to electric field and magnetic field. When V is parallel to magnetic field, angle between V and B, V cross B means VB sin theta. Angle between V and B is equal to 0 degree, sin 0 is 0, only electrical force exists. So due to this electrical force, what will happen? Only electrical force. So you can say only electrical force. So due to this electrical force, what will happen to the charged particle? Charged particle will get accelerated. So you can write 1 point. So due to the electrical force, charged particles get accelerated. Charged particles will get accelerated and moving with a certain speed. Okay, now I know charged particles will get accelerated. How I can find this velocity? We know this is moving in the x direction. So v is equal to u plus at. We have an equations from one dimensional motion. So along the x direction, vx equal to ux plus at. So what is velocity at x direction? Means final velocity starting from rest. So this is equal to 0 plus at. What is acceleration? Next steps. Acceleration is what? Acceleration is equal to force by mass. What is force? QE. So QE divided by m. So this will substitute will be here. So QE divided by m into t, which means simply Vx equal to QE by m into t. So this is the velocity at which the particles are moving, because its velocity is keep on increasing because electric field is very strong towards the right side. So whenever it is started here, electric field will be less. Electric fields are increasing in the direction. So whenever it is going forward in this direction, the electric fields are increasing higher, velocity is increasing higher. The increase of velocity is called acceleration. So in short, this is an accelerated motion. Okay, so electric field and magnetic fields are parallel. Charges are placed and initially at rest, and this charges will get accelerated. Its speed will be increases. Okay, hope this is clear to you. Okay, now a small derivative of case number 1. In another case. Another case means suppose the charge initially coming into the field with a velocity v0. Suppose initially I told the charges is at rest, then this is the condition. Suppose it is coming to this field with a velocity called, which means this is an electric field and this is a magnetic field, and a charge which is flying into the regions, the charge q is flying into the region with a velocity called v0. So what will happen to all these equations? Here up to this one no changes, electric field will get accelerated. But the point is like initial velocity here it is not 0 because it is not starting from rest. In this case, what is our Vx equation? Vx equation, initial velocity v0 plus rest of the same acceleration, force by mass QE by m into t. This is an alternate case. Suppose the charge is initially moving into the field. Into the field means how many fields we have? Two fields we have, right? Electrical field and magnetic field. When velocity is parallel to magnetic field, angle between V and B equal to 0. So there is no magnetic force, only electrical force. So electrical force directions, electrons will start to move. Magnetic field is waste. It's pakka waste. It is not contributing to any force because V and B are parallel. It has no influence here in this context. Okay, fine. Perfect. So let's move to the next one. So hope the case one is clear to you and you got some idea what it is means about it. Okay, so fine, charges are moving parallel into the electrical and magnetic force. Next we are going to see the next case. Case 2, second case. E and B parallel. Electric field and magnetic fields are parallel. Charge Q is moving into the field, moving into the field with a velocity v0, with a velocity v0, and it is perpendicular to both E and B. This is a context. Electric field and magnetic fields are parallel. Charge Q is moving into the field with a velocity v0, and it is perpendicular to both electric and magnetic field. It is perpendicular to both electric field and magnetic field. So what will happen in this case? That is the context of the discussions. So let's consider the diagram. Electric field in this direction, magnetic field in this direction, a charged particle moving into this field area with a velocity called v0. Okay, so this was a context. Next, we have to see whether there is Lorentz force context. What is called a Lorentz force? FL will be equal to QE plus QVB sine theta. So now we'll see QE. Yes, electrical force will be there. Because of electrical force, when a charge is coming will be here, electrical force in this direction. So charge can move like this. Charge can bend like this one. Plus QVB sine theta. Theta is the angle between velocity and magnetic field. Velocity and magnetic field angle is how much? 90 degree. 90 degree. If it is 90 degree, magnetic force exists. So total force will be equal to FL equal to QE plus QVB, which means the effect of electrical force is there and the effect of magnetic force will be here. Now here we have to be little bit alert. Alert means this is what kind of motion this will be lead rise to. Okay, this is what kind of motion this will lead rise to. See, a charge which is coming from here and going upward, and electrical force is there in this direction. Okay, and magnetic force. If magnetic forces exist in a charged particle, means the charged particle, if you forget about electric field, when a charged particle is entering into a perpendicular magnetic field, it will experience what type of motion? Circular motions. In the last few sessions we have learned about, right? Magnetic force will be equal to mv square by r. So if it is a magnetic force alone will be there, it will undergo circular motion, but due to the electrical force will be here, this electron will have a tendency to go like this one, because somebody is pulling it in this direction. So what will happen? The electrons coming will be here, has to undergo circular motion. At the same time, it has to move forward also. It has to move forward because of this electrical force, and it has to undergo circular motion because of magnetic force. Okay, so it is a combination of, I can say, electrical force and magnetic field force will be here. So I can say it is a combination of, what are the motion? Combination of straight line motion. Straight line motion. It's a combination of straight line motion due to, who is giving the straight line motion? Electric field is giving a motion in this direction, and circular motion. Circular motion is given by whom? And circular motion due to whom? Due to the magnetic field. So circular motion due to magnetic field, electric field motion. So the electron has to move forward, at the same time it has to rotate. So how the structures look like? The structure is look like this one. This is called what type of motions? This, of course we know, this type of motion is called helical motion. This already we have seen, right? This is an example of an helical motion. So if you are asking me very correctly, then I will redraw the diagram in a more specific way. A very accurate method is like, the electrical force when moving forward. If you are moving forward, electric field strength increases. Electric field strength increases means electrical force increases. Electrical force increases means I will pull it more fast in this direction. So what will happen? Magnetic force will be same because QVB, magnetic field will be there, magnetic field strength will be there, electrical strength also increases, so the pushing towards right will be high. In this case, what happens is like the motion is something like this one. Motion is something like this one. So here you can see the pitch. Pitch is the distance between these 2 points. P1 pitch, P2 pitch. P2 it is the distance traveled over one time period. So this is over one time period. So this is called P3 and this is called P4. So I can say it is an helical motions in more specifically with a variable pitch. With a variable pitch. Very more accurate answer is like this. So it's a helical motions with a variable pitch is performing when electric and magnetic fields are parallel to each other and velocity is perpendicular to both. Then this will execute a helical motions with what is called with what is called this will execute an helical motions with respect to what? With respect to electric and magnetic field. Helical motions with variable pitch. Okay, fine. So let's go to the next case number 3. Now we know velocity is parallel to electric and magnetic field. Electric fields and magnetic fields are parallel to each other. Then velocity is perpendicular to magnetic field. It will experiences what type of motion? Helical motions with variable pitch. We'll go to the third case number 3. Again, E and B parallel. E and B parallel. This is what we have seen so far. The charge Q is moving. The charge Q is moving with an angle theta. To E and B, with an angle theta to E and B, which means we will depict the diagram. So electric field and magnetic fields are parallel. That's the first one. E and B parallel. Charge Q is moving with an angle called theta. Okay, so let's assume the charge is moving like this with an initial velocity V0. And this will make an angle theta here. This will make an angle theta will be here. So what will happen? Next, we have to see. Now this is not parallel. Velocity is not parallel. Velocity is also not perpendicular to each other. So what will happen? Here, this velocity, suppose I am assuming it is called V, for example. So, okay, let me put it as initial velocity. We earlier put it as V0, right? We split it into these two components. One is called horizontal component, along with the theta is called V0 cos theta. And the perpendicular component is called V0 sin theta. So V0 cos theta is one component, V0 sin theta is the another component. So two components will be there. Electric and magnetic fields are perpendicular to each other. In that context, two components will be here, electric field and magnetic fields. Okay, now the point is will be here, it's simple. So V0 cos theta, so there is a electrical force will be here. Now we will write the equations for Lorentz force. Lorentz force FL will be equal to QE plus QVB sin theta. Okay, so next we will look, FL will be equal to QE plus sin theta. You see, now earlier we have this velocity called V0. V0 splitted into two components, horizontal component, vertical component. Horizontal component is V0 cos theta, vertical component is V0 sin theta. So there is a two magnetic force will be here. One is with respect to V0 cos theta, another one is with respect to V0 sin theta. So let's substitute will be here in this case. So I can say one is V0 cos theta is a velocity and magnetic field. What is the angle between V0 cos theta and magnetic field? Both are parallel to each other. So its angle is sine 0. The next because this V is splitted into two parts, that's what equation is going to split it as a two parts. One is this part and another one is this part here. What is the next parts will be here? Q into V0 sin theta into magnetic field B. What is the angle between V0 sin theta component and magnetic field? It is of sine of 90. Okay, so we know this will goes to 0 because it is sine 0. So we have only the components. So Lorentz force will be equal to QE plus Q into V0B sine theta. Okay, so this is the Lorentz force components will be here. Next, of course we know we have to calculate the velocity because we know this will get accelerated. Initial velocity is what? Initial velocity is not V0, it is the along the x direction it is accelerating. So what is the x direction velocity? X direction velocity, motion is along the x direction. So we need to calculate the x directions velocity. So this is called V0 cos theta plus QE by m into t. So this is the x directions velocity. Next, the point is again here asking, this is what type of motion? I know a charger particle is coming like this one, electric field is pulling in this direction, magnetic field will give rise to what type of motion? Circular motion. So this is again, so you can write, this is again a combination of, this is again a combination of E and B, electric field and magnetic field. Okay, so electric field will give rise to what type of motion? Straight line motion, this will give rise to a straight line. So what will give rise to B? B will give rise to a circular motions. Circular motion will give circular motion, this is not 100% correct will be here. Circular motion means velocity is perpendicular to magnetic. See here, let me come to this point with an explanations. So forget about it. So now see, V0 cos theta is parallel to magnetic field, it has no effect, but V0 sin theta is perpendicular to magnetic field. So these charged particles will undergo circular motion because of V0 sin theta, because V0 sin theta is perpendicular to B. V0 cos theta has no effect. V is not here now. V0 is not here because V0 splitted into, you can consider like V0 is a full apple. If a full apple cut into two pieces, half and half, one half is this one, another half is this one. So now full apple is not exist, only two half apples. So this half apple V0 cos theta has no effect, but V0 sin theta will have effect. This V0 sin theta will give rise to what type of motion? Circular motion. So straight line motion, and here what is called circular motions, circular motion from why it is giving circular motion from V0 sin theta. V0 sin theta will give the circular motion. So again this is combination of circular motion plus straight line motions, and this will give rise to what kind of force? This will give rise to what kind of force? This will give rise to again an helical motions with variable pitch. So this will give rise to an helical motions with variable pitch. So if it is something like this one, then this is called P1 pitch, and this is called P2 pitch, and this is called P3 pitch. Okay, so we know this is called P3. We know P3 greater than P2 greater than P1. So we can more specifically written this as helical motion with variable pitch, Okay, now I have to put a conditions to you. I am giving an extra bonus point. Suppose in the same case, in this case, when E equal to 0, there is no electric field. This we have learned, right? When there is no electric field means only magnetic field. Charged particle is entering to the magnetic field at an angle theta. This will undergoes, my last session, just the previous session of the video, this will undergoes helical motion with constant pitch. With constant pitch. This is important. JEE main students, very important. JEE main point of view, this is very important, because there are always a helical motion related questions will be there for JEE entrance examinations normally. So Neet students may not be happy. Okay, you should not be happy. Why? Because there are questions will be there from this session also for your Neet. Okay, so Neet point of view also questions will be there. So helical motion with constant pitch when electric field will be equal to 0. Helical motions with variable pitch when both electric field and magnetic field exist. So nobody cannot be happy. Okay, you can be happy if you are making a correct answer in the final entrance examination, so that for that you want to learn it in a conceptual way. Okay, there is nothing to by heart will be there in the physics, nothing, even a single point it's not available for you to by heart. Everything will be depends upon the concepts. So it's purely based on the conceptual study, nothing else, nothing wrong, nothing less. So third case is over. So let's move to the next case. Okay, learn it in a very conceptual way, so you can enjoy the subjects, you can understand it. Okay, do not by heart anything in physics at any stage, not only in physics, in all the subjects whatever you are learning. Never try to by heart, because you will not remember. Maybe after 1 or 2 years, whatever we studied we need to remember, because in your next level of degree courses you have to be thorough with what you are doing. You know what you are going to do will be there. Okay, so the next case, I think it's case number 4. Case number 4, the fourth case. The fourth case is speaking about E and B perpendicular to each other. On different case, right? E and B perpendicular to each other. Charge Q is also perpendicular to both E and B. Both E and B. So E and B is perpendicular to each other. Okay, so this line, this is not in heading, this is a different case, right? So E and B are perpendicular to each other. Charge Q is also perpendicular to both E and B. This is one of the important case out of what we have seen so far. Let's see case number 4. Electric and magnetic field perpendicular to each other. Charge Q is also perpendicular to E and B. So let's have the diagram first. So electric field and magnetic fields are perpendicular to each other. So electric field is like this. Magnetic field is perpendicular. So magnetic field is into the board. You also know cross mark indicating into the mode. Dot is out of the board. Charged particle is entering like this. The charge is moving like this with a velocity called V0 or V0, whatever it is. So I'm assuming charged particle is moving with a velocity called V0, for example. So what will happen? Here electric fields are directing from bottom, top to bottom. So you can assume here we have a positive plate. Electric field means positive charge, and here you have a negative plates. So electric fields are always directing from positive to negative, and magnetic fields are going into the board, and charge is moving from left to right, positive x direction. So whenever the charge is coming like this one, what is the direction of electrical force? So we know like Lorentz force. FL will be equal to QE plus Q into velocity is in this direction. Magnetic field is into the board. So angle between them is sine 90. So QVB sine 90. So V naught. So FL will be equal to QE plus QV naught B. So Lorentz force is clear. Lorentz force exists. So electrical force exists, magnetic force exists. Both forces are in place. So what is the direction of electrical force? So here we have to see electrical field is in this direction means electrical force is also in this direction. FE equal to QE in this direction. But what is the direction of the magnetic force? Magnetic force directions can be found using Fleming's left hand rule. So what is the Fleming's left hand rule saying? Magnetic field forefinger giving rise to the direction of magnetic field. So my forefinger is into the board, and the middle finger means electrons are the positive charged particle motion. This is plus Q and this is moving in this direction. So like this. So what is the direction of my magnetic force? Magnetic force is going upward. In your case, you have to keep your paper like this, then you have to do this work. Okay, you have to keep your paper like this, then you have to do the work. The same way, this is my board, you can consider this is your paper. So your reading position is like this one, but while you are applying Fleming's left hand rule, I recommended to keep it like this. So this is your paper, and in my case this is my board. Okay, so magnetic force, motion of charged particle, magnetic field is into the board, and as per Fleming's left hand rule, thumb is pointing to the direction of magnetic force. So magnetic force is in the upward direction. So two force will be there. Electrical force and magnetic force both will give rise to what called Lorentz force. What is a magnetic force? We know it is QV0B. So this is the directions. So there are two contexts will be here. Now we have something called special context called. For example, so I can say electrical field is stronger than magnetic field. If electric field is stronger than magnetic field, which implies to me electrical force greater than magnetic force. Which implies to me electrical force greater than magnetic force. Electrical force greater than magnetic force in the sense, what will happen? This force will be higher. So somebody is pulling a charge which is coming in the direction. Electric force will be higher than this force. So somebody is pulling downward with more strength than upward force. Upward force strength lesser. Downward force strength more because electric field is higher. So what will happen? This charged particles will undergo like this. This is a what kind of motion? This motion is called a downward parabolic motions. So this is a downward parabolic motion. So this will undergo, the charged particles undergo downward parabolic motion. In another context, if magnetic field is stronger than electrical field, then we will say magnetic force greater than electrical force. Just reverse of this one. So magnetic force is higher, electric force lesser. So what will happen? The charged particles will go upward, right? This is coming like this and this will go upward because magnetic force will be higher. So this will lead us to what is called upward parabolic motion. Upward parabolic motion. This is something called upward parabolic motion. So downward parabolic motion and upward parabolic motion. So downward parabolic motions will be there and upward parabolic motions will be there. And the fourth case is like when E is equal to B. So electrical force and magnetic forces are equal. So which means we have to say electrical force equal to magnetic force, because I am pulling in upward with 10 Newton force, downward with 10 Newton force. Both forces are equal. What will happen? A charge is coming like this one. I am pulling 10 Newton. I am pulling 10 Newton upward and downward. Both forces are equal in magnitude, opposite in direction. That will cancel each other. If it is cancelling, is anything happen to this charged particle? This positive charged particle will not go down, will not go upward. It will continue in a straight path. So we can say, in this case, we can say charged particle, positive charged particle continue straight line motion, it's continue the straight line motion. If it is continuing the straight line motion, then of course it should have an speed. So this is a special cases for me. So I need to know QE is equal to QVB. I know sin 90, charge cancel, and this velocity V0 will be equal to electric field by magnetic field. This is an important relation. This will give rise to electric field divided by magnetic field. So electric field divided by magnetic field, because electrical force and magnetic forces are equal, and both are, because of both are, it is not going downward, it is not going upward, and this is special condition. And this condition, and you can say the condition in the sense, and this is called, so this is called velocity filter. This condition called velocity filter, or you can say this is also called velocity selector, this velocity. So somewhere you see the word called a velocity filter or velocity selector. The meaning is that like that, a charged particles in a magnetic field where electric force and magnetic forces are opposite to each other, electric fields and magnetic fields are perpendicular to each other, charged particle is moving perpendicular to the magnetic field. If both the forces are equal, the charged particle is not moving upward, not moving downward. Instead, it will continue the straight line motion. Once it is continuing the straight line motion, means the charged particle, that condition is called velocity filter. Why velocity selector? Why it is called velocity filter? Why it is called velocity selector? I will tell you an example. For example, you assume like that you have 100 charges are coming, 100 positive charges are coming. You need 75th charge going to be in straight line. All other charges you want to go, you want to be, suppose you want first 74 charges needs to be go in upward direction, 75th charge alone you want to go in a straight line motion, and 76 to 100, that number of charges has to go downward. So for that, what you will do, you have an electric field, you have a magnetic field. If you are increasing the magnetic field, the charges will be moving in upward direction. If you are decreasing the magnetic field and if you are increasing the electric field, charges will move downward direction. So you can filter out of 100 charge, you can filter the 75th charge. The 75th charge you can decide, hey, you want to go in a straight line motion. Out of 100 charges, out of 100 charges of the pool of the charges, I want the 75th charge to be moving in a straight line motion and all others has to be excluded. How I can do this one? This is what is our normal filtering mechanism is doing. So we already know water filter we are using in our home. What is basically water filter is doing? Water filter is removing all the germs, all the sediments out of this one, and it will give rise to a pure drinking water. This is what they are doing, right? So all the sediments, all the unwanted things are removing, and whatever required to our body, it is filtering out and giving us, and we are drinking the water. So same way, here it is a filtering mechanism or it is a selection mechanism, and that selection mechanism is talking about a velocity selection or velocity filtering, which means you can filter a certain component of charged particles moving in a straight lines with certain velocity. That is why it is called a velocity filter or velocity selection. Okay, hope this is clear. Okay, so let's move to the next case. Case 5. Fifth case. Okay, what is the fifth case is talking about? Fifth case is talking about E and B perpendicular to each other. Perpendicular to each other. Charge Q is at rest at the origin. At the origin. So let's have a look. For example, electric fields are in this directions. E, J direction, and magnetic fields are in the direction B, K, and this is an X coordinates. So a charged particles will be here, which is will be here at the origin. Electric fields are in the Y direction, magnetic fields are in the positive Z direction out of U. Okay, so the point is like this is an X coordinates and this is a Y coordinates and it is a Z coordinates. Charges will be there. If charges will be placed at the center, so initially at rest, so charges will be moving in what direction? Y direction. So 0 plus initially rest QE by M into T. So Vy will be equal to QE by M into T. This is moving with called that velocity. Now we have to see the Lorentz force also in parallel. What is Lorentz force? QE plus Q into. So velocity will have a tendency to move in this direction. Okay, so magnetic force is exist, correct? So magnetic force is exist when the charges particle is started to move or it's moving in the direction, then I can say QVB some sine theta, some angle will be there. Okay, so whenever it is whenever it is started to move during the time, a magnetic force will be started to experience. So here I am giving, this is not the initial velocity, here I am giving the velocity called y, because once it is started, so initially there is no magnetic force because it is at rest. Okay, so magnetic force will be equal to 0. Once it is started to move, velocity will be coming to picture and velocity is in the y direction, so immediately magnetic force will start to act. Now we have to see, now there are two forces. One is the electrical force Fe in the direction, which is called QE, very clear. Next one is called a magnetic force. See, here I am writing as Vy and magnetic field is in the Z direction. You may think like, okay, one is in the Y direction, another one is in the Z direction. Sir, why you can't take theta equal to 90 degree? It's not like that. It is not theta degree. Why? Because, listen very carefully here. Why? Because initially it rested, no magnetic force, because QV be V0. Next, once it is immediately started to move, what will happen means, moving velocity is what direction? In this direction. Okay, so this is the middle finger is representing the direction of velocity, forefinger is representing the direction of what is called a magnetic force. So the magnetic force is positive Z direction, means towards you. So my forefinger is towards you and the middle finger is going upwards. You can see the magnetic forces are going in this direction, So the magnetic forces are going in this direction. So like this, and it's going in this direction. So there is a magnetic force will be here, Fp. So somebody is pulling upward, at the same time somebody is keeping a force downward. So what will happen? Now you see, because of Fe, the charged particle is moving upward. Immediately somebody is pulling. So what will happen? This will turn round. Again, somebody is pulling upward. So it's going upward. Whenever it's try to go upward, magnetic force will come. It will keep it down. So it will keep it down. It will keep it down. So this is what type of motion? This is called cycloid motion. This type of motion, sine wave kind of structure is called cycloid motion. So this will undergo cycloid motion. How should I get FB direction? FB directions from Fleming's left hand rule. FB directions from Fleming's left hand rule. In Fleming's left hand rule, a forefinger in what direction? Positive J direction. Forefinger magnetic field. Magnetic field is in what direction? Plus K direction. and middle finger representing the direction of the velocity. Middle finger in what direction? The direction of velocity. So positive J. So thumb pointing to what directions? Positive I direction. Now if you substituted will be here. Now you know it's like magnetic force is Q into V cross B. So Q into velocity is in what direction? It is J direction. So J cross K. J cross K means what? In a two-dimensional motion, normally we learn I, J, K. So J cross K, if it is in the same direction, then this will give rise to call I. So which become Q I component will come. So I am pointing only the direction. So J cross K is I. That's what we got. Thumb is pointing to the positive I direction, which means what direction? Positive I means positive X direction, right? Positive X direction. So one is pulling upward, one is pulling like this. So pulling upward, somebody is pulling like this. So going upward, immediately coming. Going upward, immediately. Going up, immediately coming down. This is type of motion is called cycloid motion. Cycloid, like a sine wave kind of motions. These are the various cases involved in the combined electric and magnetic forces. What will happen to the charged particle if it is moving in a combined electric and magnetic field? It depends upon the case. Either it is a first case or it is a second case. Now it is very clear why I am not taking as sine 90, because one immediately it started to write magnetic fields in the Z is a direction, velocity direction change. So what I told to you, initially immediately when it started to run, it is in the y direction, but all of a sudden its velocity direction get changes. So the direction velocity changes means angle between V and B is something else, not 90 degree. So remember this cycloid motion. These are the various cases available under the motion of the charged particles within electric and magnetic field at various situation. Hope this information is clear to you, and this is perfectly clear to you. Hope you understood all the 5 cases what we have discussed will be here. Okay, so thanks and have a great day.